Okay, so this is this week's MATLAB. And like I said, I actually haven't looked at this in a while, so let me see. So I'll just run all the cells. So this just clears everything. I think there's nothing in this one already running, so there's nothing really to clear. You guys can see my page, right?
Yes.
Okay. And then here I say, suppose we're wanting to do some sort of transformation and then do a change of basis, right? So I sort of explain how to do that for this particular one. Okay, and let's see. So then using this notation, so this notation is going to be the matrix of t with respect to a basis b, right? This m underscore t underscore b, right? And I want to write a function that's going to change basis to write a function to change the basis. Oh, write a function change basis standard that will take this matrix mtb together with b as its input. So you're going to give it the matrix and the basis as the inputs. Let me see. Someone's popping in here. Okay. And I think we want to make it do a change of basis. Sorry, I got sidetracked. I got change of basis. B. This is usually a matrix. Da, 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 da. Apply your and here apply your function to some choice mtb and b. For example, above you'd have this one. Ah, okay. So right. So your job is to write the function. Oh, and it's supposed to do something like this. And let's see. And I think. Ah, okay. So so I've given you a cell down here in which you're going to write your function. And it's been a little while since I've done this, but I guess the way this works is the output will be this matrix here. The output here will be this matrix MT. This will change basis to standard matrix basis. And all we're going to do is work with these variables here. And so the way this thing is going to work is, okay, so the way this first one's going to work, let's see. Here's what I'm on. Let me just make sure I understand this correctly. So you run a function that takes the bases b1, b2, b3, and b4, all those bases, and the matrix from b1 to b2, and outputs the matrix from b3 to b4, okay? Good. So it's kind of fun because working these problems ends up doing a lot of the stuff that I wanted to spend time in the class on. So we have to sort of jump ahead here, but the structure is like this. And so let me get that color. So here the notation is like this. Actually, let me just look again. Sorry. It must be like B1, B2 or something like that, right? For my notation. I swear I keep seeing someone pop in then disappear. Let me know. I don't know if you guys can see who's in the waiting room at some point. Tell me if I'm missing someone. All right, so your book would denote this like this, right? So you have some transformation and some basis, right? And then my notation for the same thing, I really don't like the book's notation because it's so bulky, would be like this, right? So that would be the notation I would use. So these are matrices, right? And so what this is I have a T going from some vector space U to some vector space V, right? And I've got B1, which is a basis for U. These are finite dimensional. And B2 is a basis for V, right? So like that. Okay, so that's the structure, right? And you've done these sort of things for the last 2 weeks and the previous DQs, right? So you've sort of been playing around with this idea, right? And then what we want to do here is take this thing, right, and actually make it into a transformation. We're going to do something to it to transform this to the matrix 4T with respect to some other basis B3 and B4, right? So that's the idea. We want to do that, right? So just on the math side, let's see. Let me just stretch this out for a second. We don't need that for a second. Let me Okay, this I want to go away. Okay, let me just blow this up for a second. More room. Okay. So on the math side, we have this sort of setting. We have u going to v, and that's t, and I've got b1 and b2. Okay, sorry, b2. And then we want to go on and change this to basis b4 for v. Here we want to have the basis b3 for u. Whoops, b3 for u, right? So that's kind of the idea here, okay? And so what is this map here doing? Well, it's really just the identity map, right? We're just taking u to u. I just want to use it for a basis transformation, right? For a change of basis, right? Map, right? And I'm going from v to v. Well, again, that's just the identity map, right? But I want to use it for a change of basis, right? And so over here, I have my basis t. My matrix for t with respect to b1, b2 is there, right? Over here, I have my identity map with respect to the basis b2, b4. There, right? And over here, right, I have my identity map with respect to the basis b3, b1 here, right? So that's the sort of structure we want that's going to do this whole thing, right? Because when I put so what happens when I put these together? Like, what does our theorem about how the matrices work together with the basis, right? So so here's the general theorem. If I have u going to v going to w, right? And I've got basis, let's say b, c, and d, right? These are bases for these various spaces. And this is t and this is s, right? Okay, so I might have these matrices there, right? And here I have this matrix S, C, D there, right? And all, if I go all the way across, right? What I have here when I put these together is what I have. It's actually S followed by T, right? We have to be a little bit careful about this, right? When I go across, because I need to do T first and then S, right? To get all the way across there, right? So I'm really interested over here in S, T going all the way from B to D. With respect to the basis, right? That's sort of the situation we're in, right? And so how is that going to, how's it going to match up with these matrices down here, right? So these are two, I'm not multiplying these yet, right? These are two separate matrices. So what does our theorem say about the way this works? Well, I can take the matrix for S going from sorry, for T, yeah, no, from S, yeah, S going from B to C. Wait, sorry, got to get my picture here right. S goes from V to C, right? So S is going from C to D. Yep, that's right. Okay, this S is going from C to D, right? And then T is going here from B to C. Right, so that's sort of the way these work. And what the theorem says is if I want the matrix for the map going all the way from U to V, right, with respect to the basis BD, that I can take the matrix for the map going from C to D, the map going from U to V, that's this one, right, going from basis B to C, right, and then this one, which is going from V to W, which is going from basis C to D, right, and if I multiply these two matrices together, I get the matrix for the composition ST using the basis B and D, right? Okay, so that's a mouthful. I think it's kind of clear from this picture what's going on. The only issue is getting the order of things correct, right? Because when you compose functions, you kind of flip around that order, and that kind of does weird things with the indices here, right? So we're kind of flipping around the order here, right? So here, what we're leaving, I mean, when we're done here, right, we've sort of thrown away the space V, and so we're only left with B and D, right? We're, you know, when we do this composition, we're going all the way across, and V kind of disappears, right? So the two bases left over are B and D, and we're getting from B to D, right? So in this sort of notation, the C's disappear, right? Okay, so there's a lot of notation. Fortunately, you're not going to have any timed test on notation. You'll have take home, right? So you can sort of work through the notation. I suggest thinking about these arrow diagrams. That kind of makes things simpler. Right. Now, in your book, the notation's different, right? So just to make this clear, your book would call this MST BD, right? And then this is equal to MSCD MTBC, right? And so some theorem in your book says that that's the way this works, right? So when we're composing the two transformations like this, we multiply the corresponding two matrices, right? With respect to all those various spaces, right? So we have 4 bases in play right now, right? So all that stuff is in play. Good. Okay. So that's a lot already. So are we okay up to that point? So this is sort of the theory, right? Now we want to get to some place where we're actually computing some stuff, right? So one of the things where we need to compute some stuff is going here, the identity going from one basis to another basis, right? Okay, so how do we get, like, I want to get this identity map going from B3 to B1, right? Okay, so I'm actually going to play this game again, right? I've got this is U on this side, right? So we've got the identity map going from U to U. This is going from B3 to B1 is the way I want this to work here, right? Okay, it's just the identity map. So it doesn't actually do anything, but its matrix representation is going to change, right? Okay. Well, how can I get this from things that I know, right? That's sort of the point. How can I get this thing? So what I'm going to do instead is I'm going to go like this from U with B3 to, I mean, by the way, there's more than one way to do this, but usually we're in a situation where there is a standard basis. So it's kind of easiest to go and look at the standard basis at some point, right? So most of the times we're in a situation like that. So that's sort of my thinking here. So I'm going to go from B3 to U, but with respect to the standard basis, and I always use E for the standard basis. Whatever space we're in, I use E for the standard basis, right? And then we're going to go from the standard basis over here. Let's see, are other people able to hear me? Beverly says she can't hear me.
I can hear you.
Okay. So Beverly, can you hear me now or not? I'm not sure if Beverly's hearing me. Let me just send Beverly a text real quick. Do let me know if I fade out or something. Sometimes you have to reconnect. There will be a recording, so I guess if you can't hear me for a second, then you can maybe go back and get this on the recording. Right, so okay, so and then here I'm going to just go to U again, right, and now this is going to be with respect to B1. So this is like a purely computational thing that I'm doing here, right? This is really just, we're just computing something at this point, right? And so here I'm interested in going, so this is all the identity map, right? So it's still just the identity map. Okay. And so here I'm going from a non-standard basis to the standard basis. And here I'm going from a standard basis to another non-standard basis, right? So we're in that sort of situation, okay? Typically, right, the basis we're interested in are going to be elements of Rn or Cn or something like that. So we say Fn in this book, right? So it's the field raised to the nth power. That's typically where our bases are coming from, right? So as an example, right, let me just give you an example. Suppose I have a basis B equals to the basis 1, 2, 3, 3, 2, 1. I'm just permuting these guys here, right? 2, 1, 3, right? I think that's okay. I think that's okay. I mean, you know, like if I were doing this ahead of time, I would check in MATLAB to make sure that was actually okay. So let's say this is B3. Let's say that U here is R3, just to make this a little bit more concrete, right? Okay, so let's say that this is B3. Let's say that B1 is this funny basis. 1, 1, 0, 1, 0, 1, 0, 1, 1, right? So this basis is kind of like the standard basis where I flip the roles of ones and zeros around, right? So that's kind of like that. Okay, when I'm trying to get from the strange basis to the standard basis, right? What do I want? What do I want that to have? What do I want? The identity of, let's say I'm going from B3 to the standard basis E, right? And I want to put in a basis. I want to put in an element represented in terms of B3. So like, sorry, this is what happens when I don't get to do the lecture first, right? Let me say one thing about computing these matrices, right? I mean, there's a lot of theory here, but there are very simple sort of computational things to keep in mind, okay? So just real quickly, again, let's go back to the slightly more abstract case. I've got a T going from U to V, and I've got a basis B and I've got a C, okay? And I want to compute TBC, okay? So the way you compute this matrix is you compute T on the vectors of B. So this is like, say, B1 through Bn here for that basis, right? And so let's say that this basis C has vectors C1 through Cm. Those actually won't matter here, but I'm going to compute T of B1. So T of this basis written out in terms of the other basis. And that's going to be, this is a vector, right? This is a column, right? It's a vector. Let's make sure we understand that, right? So I mean, I'm taking something in here. I'm taking a U element of, you know, U, right? So this space U, and I'm computing T of U, right? And then I'm writing that out in terms, though T of U is living over here in V, right? So it is uniquely written as summation I equals 1 to M, some AI CI, right? In terms of the C basis, right? Because everything in V is writable like that. T of U is in V, right? It's in the image space, right? And these AIs are unique, right? That's part of the V of the CIs being a basis, right? They're linearly independent, right? So when I write down a vector as a linear combination of those, that representation is unique, right? So that's unique, right? Okay, so this sequence of scalars here, right? That is, you know, the TU with respect to the basis C, that is those things there, right? That's at A1 through AM. Those are the coefficients you need to use on the CIs in order to get T of U, right? That's what that means, right? And so this map here is mapping, you know, from vectors in V. I guess more generally, if I just take some V in V, right? There's a unique AI CI, right? And then this, you know, if I look at V with respect to C, this set of this A1 through AM, right? is the unique representation, the unique set of scalars that's giving me a V back, right? Okay. Does that make sense? I mean, actually, that needs to make sense before we do anything else. I'm sort of, when we jump into work on a problem, I sort of assuming a lot of other stuff. But maybe this first, maybe before we start too much anything else, we need to make sure we understand that, right? So if I give you a vector, say I give you the vector here, and I give you the vector 2, 2, 2, right? So that's a vector in R3, right? What is its representation with respect to this basis here, right? So this is my V. This is an element of R3. V with respect to B1, right? Well, all I really did was I added those across, right? That's all I did to get the 2, 2, 2. I just added those across. So it's really one of these plus one of these plus one of these, right? So this representation here is really the vector 1, 1, 1 with respect to B1, right? So this is just the standard. This is, we're sort of assuming the standard basis here, right? So the representation of V, V with respect to the standard basis is just that, right? It's just sort of V again, because that's kind of what we're thinking about, right? So here I've got this, the representation with respect to B1 is that thing there, 1, 1, 1, right? To find the representation with respect to B3, I would have to do some work, right? To figure out what linear combination of those vectors gave me the vector 2, 2, 2, right? That's like solving a system of equations, right? Okay, so let me just sort of reiterate that. I'll come back and recap because we sort of going backwards and forwards here, right? So given a V and V, let me just recap this. Giving a base and a basis for V, right? We get a map which is going to take, well, it's going to take V, which is in V, and it's going to map it, right, to this representation, which is in Fm. This is an M, right? And in particular, right, if V of C is A1 through AM, right, then V is summation AI VI, I equals 1 to M, right? We're writing things down with respect to this basis, right? Again, those coefficients are unique, right? That's part of being linearly independent. Those coefficients are unique, right? So this is a map. It's well defined. Given a particular vector in V, there's a unique thing here, right? Turning that around, given any vector in Fm, there's a unique V that corresponds to it by doing this, right? So what this map is actually doing, right, just to do a little bit more of this week's lecture, is it's giving an isomorphism between V and Fn, right? That isomorphism is based on this basis C that we picked, right? So based on the basis C that we picked, we're getting an isomorphism between V and Fn. I mean, to see that it's an isomorphism, you just check things like, if I compute lambda V with respect to C, well, that's actually the same as lambda of V with respect to C, right? And if I take V1 plus V2 with respect to C, well, then that is V1 with respect to C plus V2 with respect to C. So these are easy exercises to do just based on the definition, right? So this map is a linear map, right? And it's clearly one-to-one and onto. I mean, that's what we just, I mean, those are theorems, right? I mean, being, well, I guess those, I mean, being one-to-one is because these are linearly independent, so the AIs are unique, right? That's something we learned about independent sets, right? Being onto is kind of obvious because we're mapping, I don't know, it's just, right? I mean, we're mapping an M, well, it's because they're both M-dimensional vector spaces. Right. I mean, well, I don't know. It's still using basis, right? It's because everything's representable by some linear combination. Okay. So these maps here are, so this map, I mean, that's, you really want to think about this. This map, which is taking V to VC, is really an isomorphism of vector spaces, right? It's taking V and it's kind of replacing V with the representation, which is just F to the N. right? So V may be some really weird vector space, maybe some differentiable solutions to differential functions or something like that, right? To a differential equation or something, right? It may be some strange vector space, but here we're just associating the strange vector space to f to the n, right? Rn, right, or Cn or something like that. Okay, so that's the kind of thing we're doing, right? So that's sort of lying underneath all the stuff we're doing with matrices, right? Because we're replacing these arbitrary things, arbitrary linear transformations with these arrays of numbers, right? Where is that coming from? It's coming from this, right? This is where it's coming from. Okay, so is there a question about this bit? Because we need to understand that bit before we move on to the next bit. Are we clear on that bit? Any questions on that bit? If no one asks a question, I'm going to say we're clear on that bit. Okay, and we understand it. Okay. Good. Okay, so now let's go back to the case where I have a t going from u to v, right? And I've got a basis b and a basis c. Okay. And so now I want to tell you how to write down this matrix using what we just did, right? So I want to write down the matrix of t with respect to bc. Okay. And to do that, the columns, I'm going to build this matrix a column at a time. And so just so I have something to use here, I'm going to say, again, B is going to be B1 through Bn. And I'm just keeping with the letter B, right? And C is going to be C1 through Cm. All right, so this thing has dimension n, this thing has dimension m, right? Okay, and what we're going to do is we're going to apply T to B1. Where does T of B1 live? It lives over here in V, right? And so we're going to write that out with respect to basis C. Okay. Now this is a vector, right? What is V is isomorphic here to Fm, right? Its dimension is m, right? And so this is a vector in Fm, right? So it's a vector of numbers, column vector, right? And then the next vector here is going to be T of B2 with respect to C. Okay, and keep going on across, and then all the way down to T of Bn with respect to C, right? So every one of these things in here is an element of Fm, and there are n of those, right? So this is an m by n matrix, right? And so the space of m by n matrix in your book is denoted F m comma n. Whoops, n. Right. So that's the way we write down this matrix. Okay. So that's pretty clear. I mean, there's still this bit to do, which might be hard, right? Because that might be solving a system of equations. It may be doing something like that, right? But this first step is sort of easy to write down. Okay. Are we good on that? So this is like an algorithm to write down this matrix. Are we good on that? That's the first important step. Okay. Now the theorem in the book, the important thing about this is, and let me just write this down, is that when we take BTBC, that's a matrix, and we apply matrix multiplication to an element in U written out with respect to basis B, right? Because we're going from U to V, then the result of this is T of U written out with respect to the basis C. Right, so this is sort of the main equation that's important about these matrices. Okay. So what this is doing is it's converting everything about finite dimensional vector spaces to Fn, right? It's converting everything about linear transformations going from a U to V into things about matrices, right? So it's just giving this kind of one-to-one correspondence between these very abstract objects and these very concrete objects, which are matrices and vectors and things like that, right? That's what makes linear algebra so computationally important, right? Is this sort of direct connection to matrices of numbers, right? Vectors of numbers. And if you were to go a little bit higher, tensors of numbers and things like that. Okay, so let's go back to this question I was trying to do, right? So this all got started because I'm trying to find the matrix for the identity map, right? It seems like this should be completely trivial, right? So I want the matrix for the identity map going from U to U, right? And in my example, I had the basis B and I had the basis C, and the basis B was, and I don't know, do I need to get it right? I'll try to get it right. Way up here, 1, 2, 3, 3, 2, 1, 2, 1, 3. Okay, so it was, sorry, yeah, 1, 2, 3, 3, 2, 1, 2, 1, 3, right? And my basis C was this other sort of funny basis, which was 0, 1, 1, 1, 0, 1, 1, 1, 0. So it's just like the, again, it's just like the standard basis where the zeros and ones are sort of flipped around, right? So those are my two bases, right? And I'm wanting to find the identity, right, with from B to C. And I'm wanting to do it without doing a lot of work. That's the whole point, right? I want to do this without doing very much work. Okay, so I don't want to solve a whole bunch of systems to do this, right? So what I do instead is I say, well, let's do this. Let's look at, let's look at what looks like a more complicated thing. And let's start here with the basis B, which I'm interested in. And let's put here the standard basis. Let's put here the basis C, which is what I want to end up with, right? And I just have the identity map. Okay. So what do I get there is I get that, combining these things using that equation I had above, right? The identity mapping with respect to the matrix for that with respect to BC, right? Is really, and now which one do I need to do this one first and then this one, right? So it's going to be the identity map with respect to EC, and then the identity, and first means to the right of, right? So I need to do this one first. And then here I have BE, right? So I'm going from basis B to E, I'm going from basis E to C, and all I'm doing is the identity map, right? So as far as the vectors are concerned, I'm doing absolutely nothing, right? So this is a good example of like where there's a difference between the representations and the actual objects, right? So we're playing around with the representations here and not the actual vectors themselves, right? The vectors aren't changing at all. It's just the identity map, right? But now this is actually easy. So what is the, let's see, which one of these are easy? It's this one that's easy. So what is the identity map? The matrix for the identity map with respect to BE, right? What did I just say a minute ago? We're going to take the identity map and apply it to our vectors, right? And there are 3 of these vectors, okay? So just to give these a specific name, this will be B1, B2, B3 here, right? Those will be my things, right? So the identity map with respect to B1, B2. And then the output's going to be an E, the standard basis, right? And then I want the identity map with of B2, right? I'm going to output the result with respect to the standard basis. There's not an E1, that's just an E. And then the identity map on B3 with respect to the standard basis E. Okay. But what is the identity? What is the matrix? What is the matrix representation of this vector with respect to E, the standard basis? Well, it's just that. It's 1, 2, 3, right? It's just the vectors we started with, right? So in this case, this is literally just the matrix I get by putting B1, B2, and B3 down as the columns, right? Very often, I just call this matrix B for obvious reasons, right? It's just those vectors put together as the columns of the matrix, right? Okay, so again, let's just make sure we understand. So the first vector here, B1 is the vector 1, 2, 3. Right, that was, I just gave that. That was the basis I gave you, right? So that's the first vector in that basis. So that's a vector, right? Now this is a vector too, but it's also the representation of B1, right? This is a weird situation where B1 just happens to be equal exactly to its own representation, right? That sort of funny equation happens. So when I apply the identity matrix to B1, well, it doesn't do anything. It just gives me B1, right? and then I write it out with respect to E, well, that just gives me B1 back. That's all it does, right? Okay. So that's my matrix there, right? So the matrix E identity going from B to E is just this matrix B where I'm just putting down the columns of this matrix are the elements of the basis B, right? Now, suppose I wanted to go the other direction without doing any work, right? What would I need to do to go in the other direction? So let's say that this is some matrix, right? And then I have this matrix here, BE, which is the one I just computed, right? So this is going to go from B to E and from E back to B, right? And so this should give me the identity matrix with respect to the basis, to the single basis B, right? Now, what's the identity matrix with respect to a single basis? What is that always going to be? I mean, let's calculate it, right? So this is just, when I write this, I mean B on both sides. Right, so we're going to apply the identity map to B1, right? And we're going to write it down with respect to B, right? And then we're going to apply the identity map to B2, and we're going to write it down with respect to the basis B. And then we're going to apply the identity map to B3, and we're going to write it down with respect to the basis B, right? Okay. Well, what is the identity map with respect to B1? Well, this is just B1 with respect to B, because the identity map doesn't do anything, right? The identity map of B2 is just B2 with respect to B. What's the identity map on B3? Well, it's just B3 with respect to B. Okay. You have a question, Grace?
Kind of. What do you, when you say like it's B1 with respect to D or B1 with respect to B, what do you mean by that?
Well, that's what I defined above, right? Yeah,
Yeah,
so there's a lot to
sorry.
keep in mind. So yeah, so we've got, so again, I mean, just real quickly, we've got a vector V in V, right? Just going back to the general case, right? We've
Right.
got a basis for V, right? So that's, you know, in general, I've got B1 through like whatever Bn, right? It's a basis for V, right? The representation of V with respect to B, right, is going to be those scalars A1 through AN, where summation AI BI is equal to V. Those are unique, right? Because there's only one way to get a linear combination that's going to give me exactly V, because these are linearly independent, right? There will be a way because these are bases, so they span, right? So there is a linear combination, right? So this is just giving me the coefficients of the linear combination with respect to that basis that gives me back the vector V, right?
So we're multiplying them.
You know,
And
so
this
this
some
these are
like sorry.
this is scalar multiplication. This is a vector, right? That's a scalar, right? So this is a linear
Okay.
combination of vectors. We have to be a little bit careful with that, right? So now here we are in a specific example, right? Where I'll just rewrite it again. Let me just take what we're doing here, right? So this specific example is this one. 3, 2, 1. Sorry if I write down the wrong thing, but I think this is what I had. 2, 1, 3. So now this is a specific example. Right, so that's a basis, right? I mean, you can check, you know, you can put this into MATLAB and say, what's the rank? And it'll be 3, or you can do, you know, what's the reduced row echelon form? You'll see that it's the identity matrix, or you can take the determinant, whatever you want to do, right, to see that it's a basis, right? So this is a basis for R3. And so then I'm doing this. I'm writing down the identity map with respect to that basis on both sides, right, is what I'm doing right now, right? And so that's going to be the identity map applied to B1, written out with respect to basis B, right? So this is, I'm just repeating what I had above, right? So it's here. It's really important that you write all this stuff out yourself and go through this once, right? Especially since my handwriting's so bad, right? But when I apply the identity map to B1, it's just B1, right? So I can make this is just B1 with respect to B. This is just B2 with respect to B. This is just B3, right, with respect to B. Because the identity map didn't do anything, right? Okay, now the question is, what is B1 with respect to B? Right, and now this is where you really need to understand this. This is really simple, but you've got to understand this, right? This is 1B1 plus 0B2 plus 0B3. I mean, sorry, B1 is, let me erase this. Go away. Okay, B1 is equal to 1B1 plus 0B2 plus 0B3, right? That's obvious, right? Okay, so the matrix of B1 with respect to the basis B is 1, 0, 0. There's 1 B1s, 0 B2s, 0 B3s, right? Okay, same thing, B2 is 0 B1s, 1 B2, 0 B3s, right? So the matrix of B2 with respect to the basis B, it's just a column vector. I mean, column vectors are still matrices, right? So it's 0, 1, 0. Right? And then can you guess what B3 is, right? The vector for B3 with respect to B is 0, 0, 1, right? Okay. So what is this identity matrix with respect to the basis B on both sides is always 1, 0, 0, 0, 1, 0, 0, 0, 1. So no matter what the basis is, if we're using the same basis on both sides, the identity matrix is that matrix of just ones on the diagonal, right? So that's what we've just shown, okay? Okay, I'm still in the middle of trying to compute the basis transformation from two bases for the identity map, right? We're still in that sort of ridiculous setting, right? So let me just rewrite that. So we've got a basis B, we've got U, we've got our basis E, I've got U, and it's just going back to U, and I've got a basis C, right? And what we've done is we've computed the transformation, and then again, here you have to be careful about the order, right? So, so here I'm going from the basis to E, right? And that one was easy, or at least we did it above. So the identity map going from B to E, right, was what I just called the B, right? It's just the matrix where you put down the vectors themselves as the columns, right? So in this case, it's just like if B is, God, I keep losing my B here. Where did it go? I thought I just rewrote it. Gosh, it was already that far up. Oh, come on, I just rewrote it. Oh yeah, no, it's right here, right? It's that matrix right there, right? 3, 2, 1, 1, 2, 3, etc. Right? So the identity map, the representation of the identity map going from B to E is the matrix 3, 2, 1, 1, 2, 3, 2, 1, 3. You just put those, it's just B1, B2, B3 as the columns, right? Okay, so there we're going from the strange basis to the standard basis. The other thing I was doing is I wanted to say, let's look at this. Let's go from the, this is the one I don't know, from the standard basis to B, right? And then let's go from B to the standard basis. So that'll be on this side. Doesn't really matter which side I do this on. I'll do it on both sides just to see this. So this is going from B to the standard basis, right? So this product is going to be the identity map, because when I compose the identity map, I just get the identity map. But it's going to be going from E to E, right? And that is literally just the identity matrix, right? For the 3x3 identity matrix here, right? Okay. And if I flip these around, I have the identity map going from E to B, and the identity map going from B to E, right? Well, this is going to be the identity map going from B to B. But what did we just show? That's also always just the identity matrix, right? Okay, now we know this one, right? This one we know. And this other one that we don't know, but we want to know, what does it behave like? I have a matrix times a matrix is I, and if I flip them
Like
around, I have
the
yeah,
inverse?
it's the inverse, right? Yeah, I mean, so it's like if I call this matrix A and I call this matrix B, what I have here is BA equals I equals AB, right? So B, which I don't know, no, sorry, B I know, A I don't know, A which I don't know is B inverse. Okay. Now there's a little bit to say here too. Is there just one inverse? Is there always just one inverse? So this is a theorem that's in your book from this week. So one of the theorems you had is that the inverse is always unique, right? So once I have something that looks like an inverse, acts like an inverse, it really is an inverse, right? And the proof of that was easy. You know, suppose I have A and I have two potential inverses like that, right? Well, I can do this kind of thing where I say B equals, and I'm going to do like B prime A B. Why is that? But that's because that's just the identity, right? Okay, and I'm going to use associativity, and that's this, right? But now this side's just the identity, right? And so this is just B prime, right? So B equals B prime, right? So once I have something that acts like the inverse, it really is the inverse, right? Okay. Okay, so here's the upshot of all that, right? When I want to find the matrix for the identity map, when I'm going from the standard inverse to the strange inverse, sorry, strange standard basis to the strange basis B, right? Well, I know that that is actually just the inverse of the map going the other way, right? And I know that this one is just the matrix B, where I just write down the the columns, right, for B, right? So it's just B inverse. Okay. So let's put it all together for this one case, right? Okay, so my real interest here, going way back to the beginning, is I've got this funny basis B3 going to this funny basis B1, right? The way I decided to analyze this was to go instead through the standard basis. Whoops, so U here, and then E, I'm using the standard basis there and doing that. So I'm sort of making this path through the standard basis, right? And so what I need to get this map to get ID B3, B1 is I want to use this sort of combination of things. So I need to do this one first. So, or I'm going to do this one second. So let me write it first. So this is going to be ID E B1, right? And then ID B3E, right? It's really useful to draw the arrow diagram to get the order right. Just again, it's hard to remember that reversing of order there, right? But we just saw exactly how to do this. Going from the standard basis B3 to E, right? That's going from the weird basis to E. So that I would just maybe denote as B3, like that matrix whose entries are just the vectors that are given, right? Okay. And then this one here, which is going from E to B1, that's just going to be B1 inverse, right? Like that. So I don't really have to do any complicated computation. The transformation from B3 to B1, where I do nothing, just the identity matrix, is just the product of those two matrices. Okay, and to be more specific, right? So if my B1 was this one, and my B2 was this one, I'm trying to use this notation where I'm using the same sort of notation for everything, which is either good or bad. I'm not sure, right? Right. So those are my two bases that I'm interested in, right? I'm interested in, let's call it B3 because that's the notation I had here, right? So I'm interested in the identity map going from B3 to B1, right? And so what do I need to do? I need to take, so this is going to go, first I'm going to go from B1 to E. So the identity map, whoop, and I got to do it in the right order, right? So from B1 to E, this is the part I will mess up. And then from E back to B3. Oh, sorry. No, I'm still doing it wrong. I want to go from B3 to E because this is my starting space. And then from E back to B1, right? So I'm still getting it wrong. I should draw myself that picture, right? So this one goes from B3 to E, then from E to B1, all doing nothing, right? It's just the identity map, right? But now we know this one here is the inverse. So this is B1 inverse, and this is B3. Right? And so what are those things? Well, what is B1 is just that. So this is just 3, 2, 1, 1, 2, 3, 2, 1, 3, inverse. And then this is B3 is just that. 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay. So that is our identity map going from B3 to B1. Is that. So it may be useful to remember this as B1 inverse B3 for the purpose of the MATLAB thing, right? Okay. That's already lots of stuff. I mean, we know you got to go back to the there were 4 matrices in the MATLAB thing, right? But we've done the hard part. This was the hard part. It's weird that the hard part is all about the identity matrix, right? That's sort of the weird thing here. So let me just keep this around for reference because I'm going to use that a couple of times here, right? So going back to our case, we had a U and a V. And I think we had a B1 and B2. And we had a T, right? And we had T B1, B2, right? That's part of our input that we're giving to the function, right? And I'm trying to turn this into T. And then so here I'm going to go U is going to go from B3 to U, and this is going to be just the identity map. And then this is going to go to B4. This again is just the identity map on this side, right? And so what I want here, and again, you got to turn the order around to do this right? So I'm going to have T B1, B2. Okay, that's something we're just given. And then this needs to go first, right? So it's going to be the identity map going from B3 to B1. And then the identity map on this side going from B2 to B4. Right? And when I'm done, I'm going to have the matrix for T going from B3 to B4. All right, so you can kind of follow that through. It goes from B3 to B1, B1 to B2, B2 to B4, right? You kind of see that in the notation here. So first you do this one, right? B3 to B1. Then you do this one, B1 to B2. Then you do this one, B2 to B4. Okay, so it's this product that we need here, right? And what did we just say? B3, B1, so that's this one, right? Was B, and let me just come up here and look, it's B1 inverse B3. So that's this one, right? This thing right here is just itself, right? This is actually part of the input to the function. Right, and then this thing over here is going to be like this other one, and I want to get the order right. So the second one gets the inverse. So this is going to be B4 inverse B2, like that. Okay, and this whole thing here is going to be T B3 B4. Okay. And you should see that we're almost to a point where we can put this into a MATLAB function, right? So this thing right here in MATLAB was denoted BMT B1 B2. So that's a thing you're given as input, right? This is just a matrix B2. This is B4 inverse. This is B1 inverse. This is B3. So it's a product of all those things, right? And the output is what you want. This is supposed to be the output of your function. Right. So this tells you what to do in MATLAB. All right. So maybe everyone write that down and then let's do it. Yeah, Grace, you had a question?
Sorry, I'm just trying to make sure that I'm reading all the subscripts correctly. For that last line.
That would be amazing if you are. let me try writing it more carefully. PT B3 B4.
And that B3, should that be a subscript or is that like on the?
Oh well, like so this is gonna be MATLAB code. So there's no way to subscript it, right?
Got it.
And so this is gonna be B4 inverse. Oh, and yeah, I guess okay. Let me make this MATLAB code too, because let's be careful with that. So this will be B4, matrix inverse, right? And then B2. This will be B2 because again we can't actually subscript things, right?
Right.
And this will be MT B1 B2 B1 B2. I keep wanting to do it, right? And then this will be B1 inverse B. See, I can't help myself from doing it. B3. Okay, you buy that? Let me take a picture of this. So I have it. By the way, I mean, these are not things I would keep in my head, right? I mean, I have to work these things out. So let's MATLAB. So here in this function we're going to define here, right? This is exactly what we want to do. And so we have this input, MT, B1, B2, and all this stuff, right? And so what we're going to do, and our output is going to be this guy up here. And the way MATLAB functions work is this is the name of the thing. This is the thing that's going to be output. And these are the names of the things that are going in as input, right? And all we need to do actually is type that. Let's see. I mean, I don't think it, like, unlike Python and stuff, the spacing doesn't matter here. But here I can just take, I'll just cut and paste. I'm just going to take this. No, I'll just take this. Okay, that thing equals, right? And then, and let's see. Oh, I made this too big. I can't see what I'm doing. Okay, so this is going to be, okay, so B4. And then B2. And then MT B1, B2. And then B1 inverse, B3. And that is your function. Right? That will do the change of base. And now we want to, okay. Let's see, can I run it on something? Well, let's see, let's do it on, let's just make an extra cell here. Let's do it on the example I was just using in class. So let's have, oh, I didn't actually give a function. So what do I want to make the function do? Let's make the function here. Let me choose something for the function to do. So
when
here I've got this
for ourselves. Is it going to be
Yep.
the transformations that we did in the first DQ?
I forget. Do I ask you to do a specific one? I forget. Is that what I do? Then
I
yes,
think
do that.
that's what it is.
Yep, then yes, do that. So here, I'm just going to make up one this time. So I'm going to take the B1 and B2 I had before. So my B1 is going to be, so it was 3, 2, 1, 1, 2, 3, 2, 1, 3. My B2 is going to be, oops, 0, 1, 1, 1, 0, 1, 1, 1, 0. Oh my gosh, I need some more things. My B3, let's just have these be the identity. Why not? In fact, I guess that's what I want the next thing to do anyway. So we'll just have B3, the basis be the standard basis. So B3 will just be E, right? So the matrix B1, right, is just the matrix 3, 2, 1, 1, 2, 3, 2, 1, 3. And the matrix B2 is just 0, 1, 1, 1, 0, 1, 1, 1, 0, right? So that's the matrix B2. And in this case, B3 equals B4. The matrix B3 equals the matrix B4. These are just the standard basis, so this will just be I, right, like that. Okay, so let's do that for our example. Oh, sorry, I didn't say what the function is going to do. What will the function do? Okay, so let's have the function do something silly like this. Let's have 3, 2, 1 be sent to -2 times 0, 1, 1. Right? And let's have 1, 2, 3 be sent to 1/2 1, 0, 1. And let's have 2, 1, 3 be sent to 1 times 1, 1, 0. Okay. So it's behaving sort of like what we'll see later when we do eigenvalues, but the vectors aren't the same. So it's not literally the same as eigenvalues, right? And why does this work, right? This was a theorem we had before. If I take any basis, I can assign it any way I want to, right, into the other vector space and extend that to a linear map by using linear combinations, right? So I can always extend this to a linear map. And since I have a basis on this side, and I'm not multiplying by 0 anywhere, I'm going to end up with a one-to-one and onto map here, right? Okay, and so the matrix of this T with respect to B1, B2, right? So again, let's just work it out. So it's T of this thing. So let me call this one B1, let me call this B2, and let me call this B3. So it's T of B1, right? With respect to this basis on this side, which was B2, right? And then it's T of B2 with respect to B2, and it's T of B3 with respect to B2, right? And so, well, what are these things? What is T of B1? Well, that's just lambda times this first vector here, right? So let me call this C1, C2, and C3, because I don't want to rewrite the whole thing, right? So the matrix is lambda C1 with respect to, not lambda, -2, -2 C1 with respect to B2, right? And then it's 1/2 C2 with respect to B2, and then it's 1 C3 with respect to B2, right? But what is C1 with respect to B2? Well, it's 1, 0, 0, right? Because it's one of these, none of those, and none of those, right? So this is -2. Again, I'm multiplying by -2, so it's -2, 0, 0. And this one is 0, 1/2, 0, right? And this one is 0, 0, 1, right? So that's my matrix, right? Going from B1 to B2. Okay. So let me put all this into control this. actually, let me just slide this up. Sorry, I can't see you for a while because I have that sitting in front of you. So if you say something, let me know. Okay, so B1 is, you can see me typing, right? You have to answer by voice.
Yeah, we can see you.
Okay.
Yeah.
Okay, so B1 is, let me just look. So it's 3, 1, 2.
Is that should that be what ours looks like? Or is that something else?
So what I'm doing now is I'm just making up an example, but I forget exactly what you're asked. I think someone said you're asked to do the example you were given for a previous DQ,
Mhm.
right? So you want to choose your basis or whatever for that DQ, right? Your matrix and all that stuff, right? The stuff you did then.
Our DQ doesn't have a line at 16. So like where would we type what
I just added that. You can add a section break right here. You can always add sections. Yeah, add sections. And then that next one is 2, 2, 1, I think. I'm not misreading my own handwriting. And then 1, 3, 3. Okay, so that's my B1. And let's do it like I always do, make them pretty. We'll just show it. B2 equals, and this is 0, 1, 1. 1, 1. Oops. That's right. Let's just make sure that looks right. Okay, so those are my two matrices there. That's good. And then MT B1 B2 we said was equal to, so that's a diagonal matrix. So this is sim. It was -2. So if you want to make a diagonal matrix where they're n by n, you can just do diag and then do a vector of length n. It'll do the diagonal matrix like that. And if you have a diagonal matrix and you run diag on it, it gives you the diagonal of that matrix. In fact, if you take any matrix and run diag on it, it'll give you the diagonal of that matrix. So that's a useful operation to have. So let's just make sure that's right. Right, so that's the matrix I had there. Okay, and then my B3 is equal to, and if I want the identity matrix, you can just write I3. And my B4 is equal to the identity matrix. Okay, so those are all my matrices here. Oh, and I didn't make those pretty, so let me make them pretty. Actually, I can just do this. Okay, so there's all of those things. And here, B3, B4 equals, so it should be this thing, change base, so that function right there. And there's my function right there, right, that does this. Let's see, how can I test it? Let's try to test it somehow. So I'm gonna make another section break. So this should be the thing that does what that earlier matrix said it should do on the standard basis, right? So if I take this matrix and I apply it, so it was supposed to be moving vectors from here to scalar multiples of things in there, right? That's what it was supposed to be doing. So I want to apply it. So this is my matrix B1. That's what I get. right? If you look at that, I get -2 times the first row, 1/2 times the second row, and 1 times the third row, which is exactly what it should do, right? So that's another thing you should do when you're doing your MATLAB is maybe do some checks to make sure it's doing what it's supposed to do, right? Let's see, and I think actually by doing that, I mean, what does this do when I'm taking these two to be the identity matrix? Then I'm doing the change of base. This thing is actually just doing the change of base to the identity matrix, right? So this is giving me, let's see. Whoops, someone's just trying to get in. Oh, I thought someone was trying to get in again. Right, that final matrix I got there was really T EE, right? So that's the one I usually just denote T. So with respect to the identity matrix on both sides, right? Good. Okay, so there's the explanation of the MATLAB together with a lot of stuff that we were needing to do today anyway. Okay, so let me take a pause real quick and just see if there's a question.
Would you mind pulling up the code for the MATLAB one more time?
Nope, I'll do that.
Thank you.
Let's see, can I make it bigger? How do I make it bigger?
Is there any tools like that we might need to like have installed for this? Because I keep getting an error at like line 15, which is
This?
yeah.
I mean, does the error say anything or just?
It says error using it has too many input arguments, but I haven't touched it, and I don't think you've touched it either.
Oh, well, you haven't. I think you haven't defined this yet, right? So here.
Yeah.
So there should be 3 inputs for this. I see here, right? This is not quite right. So actually here, maybe the change should be here. Since you're using the same B everywhere, it really would be better to be like that, right? So you see there's a problem with this function because this is just a 2 variable function, right?
Yeah.
So that's the issue there.
Okay.
Right. How can you define, I mean, this is a good thing to do. Suppose I had one basis here, right? So now I'm in the situation where B1 and B2 are the same, because that's this case, right? Where B and B are both the same, right? And B3 and B4 are I, right? So I could just write this function, or I could reuse this function I have up here, right? In this case, right? Because I could here say MT equals, and our input here is going to be MTB. So I'm going to do the change of base. And I'm going to put in MTB, right? And now B1 and B2 are just B, right? And B3 and B4 are just the identity matrix of the correct size, right? So how can I do that? Can I do like I? How do I make the identity matrix? Sorry, maybe I don't want to do this in real time. I'm trying to think, how can I make the identity matrix a function of B? There's something I don't remember. It's size. Maybe one of you know this. Let's say B1. Is it size? 3, 3. So if I say S equals, you can't do things in MATLAB that you can do with Python, which is annoying. And then I say N equals S1. Just make sure that's right. Nope, doesn't like that. What's it not like? Oh, no, it doesn't like that. That's Python again. Okay, so it's giving me that size. Let me just copy that little bit of stuff. So, oh, I got to do that up here. So I'm going to grab the size of B. And then I'm going to call this I in. Right. So this will take the matrix with respect to B on both sides and output the result with respect to the identity on both sides. But this is, so these are just the basis of the standard basis, right here. So you could do that. I mean, you could do other things here too. Like you could just write down the right formula with B, right? You could do that instead. Which is worth doing. I mean, let's just think about that because it's a separate case. I mean, so that's one way of doing that. Let's think if we had TBB. So we have just going from B to B, right? And I want to change this to T, standard, right? So in this case, I usually just write T, right, like that. Well, so what are you really doing? You're really going from E to B using the identity, right? And then you're going from B to B using T, right? And then you're going from B back to E using the identity. All right. So in terms of multiplying things, like I do this one first, right? So it's ID EB, and then it's this thing here, T B, and usually if it's B on both sides, I just write B once there, and then over here I've got ID going from B to E, right? And we know that this is just the matrix B, right? This is the matrix we were given. And this is the matrix B inverse, right, like that. So that's another perfectly good way of doing this code, right? I mean, that's actually simpler in some sense. So I could, instead of writing all that stuff, right, write MT equals, that's it's B, so B times MTB times B minus 1. All right, I could do that. Oh, do you need to see that? I mean, you'll have the video, but you can see that. Okay, do you think I have any more questions about that? Or do you think we have answered all the questions?
Will this video be posted? Because I was not hearing early on. The MATLAB one.
I will post this video.
Okay, thank you.
It would be really good if I'm forgetting to post things early that you remind me to post them.
I will.
Because like I forgot to post your homework until like today. I mean, Thanksgiving came in, and but the video, it takes a little while for me to upload it. It's kind of weird because anyway, it takes a little while to do. I have to basically download it and upload it twice to get it to YouTube once for some strange reason. So that's a bit of a pain. Wow, okay, that was a lot of the class. Any other pressing questions you had? That was a great question. We got to spend some time and learn some good stuff. Any other pressing questions you have before maybe we go on to other stuff? I'm trying to think, what was something, let me just say, so I have graded a lot of the DQs. Is it the DQs? I think it was the DQs. And one thing I feel like some people are doing, I mean, you can nod or you can keep it a secret if you want, is trying to go out and search for other ways to do things. In particular, when they have the projection ones and stuff like that, it looks like people are going out and trying to use projection formulas and things, right? You can do the same thing with rotations, right? There's rotation formulas. Those are all kind of confusing formulas, right? What I really want you to do for this section and for the exam is do this kind of two-step procedure, right, where you're sort of saying on these subspaces, right, whatever transformation you're doing is behaving very simply, right? And then you're going, so let's say I had a plane, right? Here's the origin. I have some sort of line going through that origin, right? And this plane has a couple of vectors like this, right? And then this line is along a vector, right? So let's say this is U1, U2, U3 for the line, right? And then your function is like projecting along this line onto the plane, right? So not perpendicular to the plane, but along the line onto the plane, right? So if I'm over here at some other point, I need to find the line in space parallel to that line. And if I take a point out here, it's going to go down until it hits the plane, and that's where it's going to hit, right? So you imagine you have like a field of things hitting the plane at some angle. Imagine rain hitting a flat surface at some angle, right? Something like that, right? I don't want you to go out and find some sort of weird projection formula that someone else has figured out for this, right? I want you to use, right, this is the basis, U1, U2, U3, where the plane, let's call it P, and L, so, the whole space, R3, is equal to L plus P, right? And the operation is very simple. On L, it just sends everything to 0, right? So in other words, L is the kernel of this operation. It's called this operation T. Right, so the kernel of T is equal to L, right? And what happens to points on the plane is they just sit there and do nothing, right? They're just fixed, right? So if you want to come up with the matrix of T with respect to this basis B, right? And I have it in this order, so U1 and U2 are just fixed, right? So this is going to be T of U1, with respect to B, T of U2 with respect to B, and T of U3, right, with respect to B, right? Well, this is just U1 with respect to B because you don't do anything on the plane. This is U2 with respect to B because you don't do anything on the plane. And this is 0 with respect to B because that gets mapped to 0, right? And so, this is 1, 0, 0, 0, 1, 0, 0, 0, 0, right? That's that, right? And so to get the map with respect to the standard basis, you do the same transformation we just did. It's going to be B, and then this thing here. And now you can check it with your MATLAB, B inverse, right? That's the computation you do. No projections, no funny business using geometry, none of that, right? Just change of basis, period, right? This is very, very general, right? There's no like little tricks you have to remember for a rotation, for this, for something else, right? This is just always works every time, right? I mean, the trick here is recognizing where your map is doing something simple, right? And that's kind of the part that, so do you understand what I'm saying? So lots of you, I made that kind of comment on your thing. But on the exam, I'm also warning you, it's fine to use AI to learn stuff, but it will give you methods to do things that we have not touched, right? And if you use a method we have not touched, first of all, it needs to be something that's relevant to what we're doing, not something random. Secondly, if I think you probably don't actually know it, I'm going to ask you to explain every detail of it, right? So in other words, only use stuff you actually understand, right? Okay. Yeah, maybe we should do the administrative stuff so I don't forget. So I did put up a note about the exam. Okay, so the two classes are going to have a similar structure. They're going to be 8 true false, each one worth 10 points. This is in the announcements, right? So you don't have to write it all down. Part of that will be in class, so you'll do those 8 true false, just the TF in class, right? And that'll probably be on a Google Forms thing. Sorry. And then after that, I will give you those true false questions to add to the other test questions you had, right? And then you're going to do the justifications for those things, right? That'll be the other 5 points for each of those, right? So it'll be 40 points in class, 40 points for the justifications, okay? And you don't want to justify something that where you were wrong, like if later on you realize, I said true, but it's really false, right? Then on the take home part, write false and justify the false, right? Justify whatever is correct, right? Don't try to justify something wrong, right? And then I think there's going to be 4 15 points, so slightly easier questions, which may be some computation, might be some proof, or something not slightly easier, right? And then there'll be 4 20-point problems. And then we might have it so that you can choose 4 out of 5 or something like that. We're still discussing that, but the basic structure is that. So it's 4 15-point, 4 20-point, 8 10-point true false. You will have a week for the take-home part. Okay, so I'll give it to you next Thursday, and you'll have all through I'll give it to you this Thursday, and you'll have all through next Wednesday, right, to get it done. Okay, we'll meet on Monday, and you'll do the true false part in class, and you can ask questions and stuff like that. The other thing you have is a project, okay? So the test is still going to be due on the Wednesday, next Wednesday, but I'm going to let you have until that Sunday to finish the project, right? So focus on the test first, obviously. Read the thing I said about the project. So it's a good chance for you to show off your teaching, but you do need to pick something that is not just something we're covering in class. It's got to be off to the side, in addition to, going beyond. I mean, something like that, right? It's got to be something, not just something we're doing in class. It's got to be something else. You can work in groups of up to 2. I'm going to restrict it to 2. If you do work in a group of 2, I do expect, sort of twice the amount of project to be done, go twice as far in depth or something, right? And then there's some instructions about what needs to be turned in. There needs to be a set of slides. There needs to be, and the slides should have some examples and stuff. I mean, it's like you were doing a lecture. It should be self-contained. Keep that in mind. It should be self-contained. You're not talking to me, right? So in your video, you should be talking to a class, either a class you're teaching, or say you're teaching it. I think a good thing to do is think of yourself as teaching it to your peers here, right? So that's a good target audience, right? So they know the stuff you've learned in this class, right? That's sort of where everyone is. So you can assume they know that, right? So you don't have to do everything, but assume that knowledge is known. And then whatever you put on top of that, you need to explain completely, right? So not just say, don't just say things without actually giving information, right? Like actually explain why things are true, give proofs if there needs to be a proof, explain how things work. If you need to do some applications of whatever you're doing, you don't have to go into depth on every application, but go into depth on at least one, right? Don't just say this can be used for this list of things, right? At least say something about at least one of those applications that has some depth to it, okay? And then there should also be a set of problems that you would give, say, to your class as homework associated to this thing, okay? It's only a 15 or so minute presentation, right? So it doesn't, you don't want to do too much, right? Pick something that's interesting, that has an application, that's not too hard to say everything about in 15 minutes, right? I mean, we tried to do one MATLAB problem. We've used an hour and 30 minutes, right? So, I mean, you got to keep the goal kind of small, right? Okay, so anyway, read all that. For your DQ this coming week, the first one, by then, if not earlier, give me your project ideas, okay? And what I'm going to do is I'm going to make an announcement where I'll have everybody's taken project ideas and who's in groups and stuff like that. And once an idea is taken, you can't have it anymore, right? So I don't want, if you're working in a group, you can both work on the same thing, but I don't want 2 separate groups doing the same thing. Okay, so the earlier you give me your idea, the more likely it is you get your idea, right, to work on. If you give me an idea someone else has had, I might say, well, this other person's doing that, see if you want to do a group, right? Do that as early as you can, but definitely by the due date of the next DQ. And then the DQ after that will be like a little, and now I might say that's not enough, or that's too much, or something like that, right? So we may have to refine it some. And then for the next DQ, you're going to give me like a little pseudo outline. It doesn't have to be real deep. Just sort of let me know sort of what you're going to do, right? So those 2 DQs next week will just be kind of about the project. Sound good?
I have a question about the project.
Yep.
So I know that we have that list of competencies that's attached to the assignment. So we select one of those, and then
I actually totally forgot about that list of competencies. I would say you can look at that for some ideas, but if you have something else you're interested in doing, do that. Some of those competencies are so small that it's kind of hard to do anything with them. So, I mean, like that'll come in like the approval stage, right? But if you want to do something different, feel free to go off that list of competencies. We had to put, we're getting adjuncts for these classes, so we had to put like everything set up for an adjunct. But I'm more than happy to let you go outside of that list of competencies, right? On the other hand, if you find something there you really like, you can use it, right? I seem to remember thinking those competencies were a little too vague or shallow for a real project for some of them. Some of them are really silly. Right. So anyway, yeah, I mean, just aim at your class as your audience instead of aiming at like a class of 6th graders or something, right? So, aim at someone at your level. Good. Yeah, if you have any other questions, email me or whatever, right, for that. Okay, so we're done with that. Anything else you want to ask before I try to start talking about some other stuff? My voice is really going today, so we'll see.
The D2 that we just did with the maths lab, it says due Monday. That's tonight. I don't think it says yet, but we can do.
I mean, get it done by Wednesday. I'm never counting DQs late, so to speak, right? And in fact, if you go back and do your DQ later, I'll go ahead and give you points for it, right? I mean, they're all kind of important, so just try to do them on time. But yeah, this one on Monday, I mean, there's too much stuff going on Monday, right?
Yeah.
That's fine.
Okay, thank you.
Yeah. Okay, so I did make some notes for you again. I made, again, kind of a fill in the blank thing. Again, just kind of going through the text, right? Let me just sort of point to some of the stuff we just did. A big section of the notes is on matrices and change of basis and all that. That's basically what we just did, right? So in some sense, we covered this whole section of the notes here, which is actually a fair amount of it. I didn't do any proofs of like why things are true, right? And I think an important thing to sort of look at is why matrix multiplication is what it is, right? And the reason matrix multiplication is what it is because it makes this thing true, right? This thing that you want to be true here. V B equals T of V C, right? I mean, so in these notes, I sort of argue why this is true a little bit. And, it definitely hints at why matrix multiplication is defined the way it's defined, right? Maybe I'll just say something about that. So when we're doing this kind of thing, we're in a situation like this. And then this is VB is a vector that's like this, right? It's like A1 through AN. This would be VB, right? There's n many things in the basis B, right? So there's n many entries here, right? So there are n things across here and n things here, right? And so there's lots of different ways to define matrix multiplication, but here the important one is when I'm taking a matrix and multiplying by a vector, it's really just taking the linear combination of these vectors. A, N, C, right? So that's, the result of this thing is that each of these things are in our M or FM, right? So the result is, of course, in FM. Right. So that might not be your standard way of thinking about matrix. So as an example, I do 1, 2, 3, 3, 2, 1. Doesn't matter what I put here. 1, 1, 1. Right. And I multiply by 4, 5, 6. Right. So what I'm saying is one way of multiplying this is do 4 times 1, 2, 1 plus 5 times 3, 2, 1 plus 6 times 1, 1, 1, right? That's equivalent to what you usually see as the matrix multiplication. And that's what's being used here in a relevant way. Okay. Anyway, so that's the only other stuff that's there, right? So that's there. Trying to think which part of this do I want to say anything about. We've only got 20 minutes, so it's not much time. As usual, there's just a lot of information here. One other thing I was thinking about. Some of you in your work are doing by hand inverses, right? And you're taking A and you're sort of lining it up with I and you're doing a bunch of stuff, right? There's really no need to do that, right? I think you can do that without any problem. So, feel free to go, into MATLAB and enter your matrix and enter A inverse, right? And get the answer, right? I'm not really interested in seeing you do by hand Gaussian eliminations or by hand matrix inverse computations, right? Or by hand rank calculation, et cetera, right? I mean, if I give you a echelon matrix and say, what is the rank? Then I expect you to look and count pivots, right? Something like that. Like I wouldn't expect you to go enter that into MATLAB and say rank, right? I'd expect you just to look at the pivots and say, oh, there's 4 pivots, so the rank is 4, right? So you want to use sort of the stuff we're doing. But that very sort of computational, lots of numbers stuff, right? There's so much room to make silly mistakes there, right? I'd rather you just do it with the technology, right? I mean, that's really linear algebra is meant to be done with technology. It's not really meant to be done by hand, right? I mean, like this is why what is the GPU company that's making so much money? And that's all they do is linear algebra, right? I mean, basically they have these huge matrix multiplication devices, right, that you use for everything. Anyway, that's just a thing to say. So the first section of this is about invertibility and isomorphisms. Does anyone have, I guess, first of all, do any of you have a question about that? I guess there's a couple of things I find sort of particularly interesting. But any sort of generic questions you have on that section before I say what I think is interesting? Okay, so I'll tell you what I think is interesting. First of all, a function is invertible if and only if it's a bijection, right? You know that, right? So there's nothing interesting about that. I mean, it's interesting, but that's an interesting set theoretic fact, right? Not an algebraic fact. It is very interesting that a invertible linear function is linear, right? So that's not for free generally. Like if I have so a linear function later on when you do the next class, you'll call those homomorphisms, like from groups to groups and rings to rings and stuff like that. Generally, a bijective homomorphism is not going to have automatically its inverse being also a homomorphism. That kind of thing typically fails, right? It just happens to work for linear functions. So this is sort of another special thing about linear maps. So just sort of keep that in mind, right? So if t from u to v is linear and bijective. So bijective means it's surjective and injective. So it's 1-to-1 and onto, right? Then T inverse going from V to U. So T inverse definitely exists, right? We know T inverse exists because this is 1-to-1 and onto, but it is also linear, right? So that's sort of a nice fact that comes up here, right? And the proof is kind of, I mean, what do we want to show? We want to show, I'll do part of the proof, right? So I want to show, for example, the T inverse of U1 plus U2 is equal to T inverse of U1 plus T inverse of U2, right? Let me change this to V's because I have V in U, so let me call these V's. Right, so that's the sort of thing I would like to show. Well, how could I show that? Could I just apply T to both sides? So there's kind of a question mark, right? I haven't proved it yet, right? So I apply T to both sides. Oops. So I still have this kind of question mark here. All right, like that. Well, on this side, I have T and T inverse next to each other. So this is just giving me the identity. So this is just V1 plus V2, right? So that works, right? And then on this side, well, this is a linear combination, so I can move that through. Right, but then this turns into V1 plus V2. Right, so this equality is actually true, right? So I know that equality is true. If this equality is true, right, then that would happen if and only if this equality is true. Right, and that'll happen. Well, I guess, I mean, what do I want to say here? I guess what I really want to say is this. Let's just go this way, right? So what I've shown is I've shown that T inverse, sorry, what I've shown is this, that T of T inverse of V1 plus V2 is equal to T of T inverse of V1 plus T of T inverse, whoops. Let me rewrite this. T, dang it, T inverse of V1 plus T, sorry, no, this is what I really wanted, V2, right, like that. So that's what I just verified up there, right? Right, I started with this, right, applied T to both sides, got that, right? Why does this allow me to say that T inverse of V1 plus V2 is equal to T inverse of V1 plus T inverse of V2? Which is what I want to prove, right? That's what I actually want to prove.
Because it's like they're both the inputs of the same function.
Okay, good. So let's be a little bit more specific. So if T of A equals T of B, how do I know A equals B? Right? That's sort of what's going on here. I mean, what do we know about T that gives me this? It's got an inverse, so it's bijective, right? And what does this correspond to?
Is it because it's
N1?
Yeah, it's 1-to-1, right? So this is corresponding to 1-to-1-ness, right? So if I apply T to both sides and get the same thing, then the thing I applied T to has to already be the same, right? Okay, so that does it, right? So that says that this is actually equal to that, and that gives me the additive part of being linear, right? Okay, and the multiplicative part is scalar multiplication part similar, right? So like that. Okay, so that's an important thing. Suppose T from U to V, and these have the same dimension. Okay, so we know that T is invertible if and only if T is 1-to-1. But if I'm in a finite dimensional case and these have the same dimension, what can I add to this list?
You know that they're on two because they have the same dimension, therefore nothing's going to the null space.
Well, so I mean, being sorry, I didn't say 1-to-1. I should have said bijective. Let me, oops, let's go away. I jumped the gun a little bit. So this is what we know. T is invertible if and only it's bijective. That's what I just showed, right? But we can add to this list T is injective, because we know that if we have an injective map between two vector spaces of the same finite dimension, right, they're actually also surjective, right? So it's like automatically bijective, right? And then we can add to this list also T is surjective for the same reason. Right, so get all these things are equivalent to each other, right? For finite, and you got to be careful for finite dimensional vector spaces with the same dimensions, right? So that's an assumption there, right? So this doesn't hold for infinite dimensional vector spaces. Okay. And the book gives a nice example of why that fails. Let's see, another important thing is this, that if I know, and this is another thing that fails for other algebraic structures. So this is, you have to be careful when you go to the next class, because you use matrices for a lot of examples, but also matrices have some properties that other algebraic structures do not have, right? And here's another one. So if I have T and I have S, and TS equals I, so they're sort of looking like inverses, and let's see, what do I want to say? I want to say something else. And I guess I want them to, I want to be able to switch the order. So if I switch the order in, okay, so let's stick to finite dimensional. Let's see, I guess it doesn't matter. I could switch the order. Yeah, okay, same dimension. Sorry, okay, let me add something here. So T going from U to V. Okay, so S going from V to U, and dim U, whoops. Actually, now that I'm thinking about it, I'm not sure if I need this, but let me just keep it for a second. So let's say I have the same dimension, and I know that I have this. So this is sort of saying that S is a right inverse of T, right? It's not quite saying it's an inverse yet, because to be an inverse, it also needs to be a left inverse of T. Okay, but can we actually get that it is actually an inverse of T, right? Can we actually show that ST equals I? Or something along those lines, right? Yeah, I guess I am going to use the same dimension. I'm going to use that. So what do I know if TS is equal to I? What property can I say S has? Like TS is the identity matrix. So it's one-to-one and onto, right? Now it's a composite function. So what part of that goes down to S? Can S fail to be injective? I mean, if S maps two things to the same thing, right? That would what it means to fail to be injective, right? Then so would TS, right? I mean, we've got here, U, we've got V, we've got U again, right? And we have, let's see how mine is going. Let's see, sorry, let me turn it around. V, U, V again to make my picture work, right? And I'm doing S first, and then I'm doing T, right? So the picture is sort of like that, right? Sort of a algebra 2 picture of functions, right? That kind of thing, right? If two things got mapped to the same thing here, then their composition definitely will map to the same thing, right? So if TS injective implies S injective, right? On the other hand, if S failed to be surjective, sorry, this is T, right? If T failed to be surjective, right, then ST would, right, if the range of T was just this stuff, right, then ST would also fail to be surjective, right? So the fact that TS is bijective implies that S is injective and T is surjective, right? But the fact that these have the same dimension, V and U, if S is injective, what do I actually know about it?
That's a one-to-one.
It's got to also be surjective, right? So if I have an injective map between two, injective linear map between two vector spaces of the same dimension, it's got to also be surjective, right? Okay. And same thing for T, right? So what we actually know, just by this thing being I, we actually know that T and S are both actually themselves injective and surjective, right? By this argument. So we actually get that for free using this dimension property, right? Using the fact that we're dealing with finite dimensions. Okay, but what does that tell me? It tells me that, say, T inverse exists, right? But once I know T inverse exists and I have this, then I can actually do some algebra and say, well, T inverse TS is equal to T inverse I, right? And then we can use, then we can use some associativity, right? But on this side, I just get S, because this is IS, so I'll just write it. This is IS equals T inverse I, right? But this just says S equals T inverse, right? Okay, so once I know they're invertible, I can just prove using some algebra, right, that S is actually T inverse there. Right, and then once I know that S is T inverse, then I also know that S, let's see, I was given, I forget which, yeah, I was given TS equals I also know that ST equals I, right? So I'll know it in that direction too. So this is an important fact. I mean, it's a useful fact, right? If I know I have two matrices where these multiply together to give me I, right? Then I actually know already that B is equal to A inverse without having to check that BA equals I. Okay. This maybe it seems trivial too, but it's not clear really, right? And we'll definitely see an example later in the class where this is useful in a way that it's not at all clear that it should be true. Okay. Anyway, those are important things. 5 minutes. Let's see. Yeah, I don't know. I don't really want to say anything more about that. I'm going to say read this, try to fill it in. If you have questions, ask. The quotient spaces you don't do a whole lot with in this class, but they're like a major theme of 513. Okay, all over the place, everywhere. Use quotient spaces, quotient groups, quotient rings, quotient field, everywhere. Use them. So it's worth learning it here. Okay, so take a look at that anyway. Right. I think it's a good place to stop. And my voice is really about gone. So let me just see, are there any other questions you have for me that you want answered? I'm not getting a lot. Everybody's good. Everybody's good. Thumbs up, everybody. Okay, good. All right. So as always, you can schedule meetings with me if you need to, and I will see you next. Actually, let me do one thing before you go. Let me do one thing. Let me just capture a screenshot so I know who all's here. Okay, now you can all go. All right, have a good dinner or whatever it is for you.
Thank you.
Professor,
Bedtime.
Thank you.
See you.
can I ask you a question about the DQ real quick?
Yes. Who's talking? I can't even tell who's talking.
It's me, Joseph.
Oh, Joseph. Hey, yeah.
Yeah.
Yeah, what's up?
So I know you've been responding to the first DQ, and I'm just wondering, because I guess I did use like a different method, and I was looking through AI just to get some idea with the question, but I did eventually respond with using the change of basis. I'm just wondering, is there anything else that I need to do to get the credit for the DQ, or are you just asking me to like cut out the part from my old work?
Yeah. Oh, I see what you're saying. Yeah. It's
Yeah.
the logic in your answer that bothers me, right? Because you have
Okay.
all this work that sort of where in the end you get this matrix, right? And all this work is that sort of like does not apply to what we're doing.
Yeah.
Right. And then down here you
Yeah.
get TB, you get the nice simple matrix, right?
Yeah.
And then you go and you do the right thing and you get T again down here, right?
Yeah.
So this is the
Yeah.
part I'm interested in, right?
Yeah. So
I just want to make sure that this
yeah.
is.
So did you want me to just delete that? Because I initially just didn't want to take out the old work because I was like, oh, okay.
Did I not give you credit for it? I thought I gave you credit for it.
I don't think, unless I haven't changed, but I can check again. Yeah, I still haven't. It still haven't been updated.
Well, let me see. Oh,
Yeah.
Okay. This is DQ topic 3 DQ1.
Yes.
Is that it? Okay.
Yeah.
Because I thought I just made that as a comment. Yeah, it might be that I just haven't assigned credit to. Oh yeah, no, I see. I didn't change it. Yeah, I really just meant that as an additional comment. So I wasn't actually asking you to make another change.
Okay.
So it's updated now.
Thank you. Sorry.
No, that's fine. Some of the rest of you, you're hanging out. Is there something you want to know?
I have a quick question about the take-home quiz.
Okay.
One of the things that I do for like the DQs and the homework is I'll try everything like as far as I can get on my own, and then I'll put in like AI. I'll say, here was the question, here's what I've got. Are there any like errors, or did I mess up some notation or vocab? Is that something that's okay to do?
I think
Like,
that's fine. I mean,
okay.
Again, it's good to ask I mean, first of all, I can't really control what you're doing when you're doing a take-home test, right? The thing I want to see is I want to see that you actually understand what you're doing, right?
Yes.
And the danger of using AI, and it happens for me too, because even sometimes when I'm doing stuff, not so much for this class, but for 512, students do things all the time that I'm not quite sure if they're true or they're not true, or and I have to go to AI too and just use it as a partner to figure these things out, right? And often it'll give me some crazy theorem that says this isn't true because of this thing that I don't understand, right? And so I have to keep saying, can you just just use these results, right? Just try to make, and you keep kind of whittling it down till you get it to something you completely understand, right? And then write down what you completely understand, right?
Okay.
And in doing that, you've learned something. So that's kind of the point, right?
Okay.